Hello everyone, welcome back to the Organic Chemistry playlist. In this series, we're looking at radical chemistry. So this is more the introductory video, but we will get into what radicals actually are in the next coming segment. But basically, these videos are going to follow this format here. So we're going to look at what are radicals. Monohalogenation, so adding a halogen to an alkyl group. The selectivity of halogenation. We're going to look at allylic bromination. We're going to look at HBr across an alkene with using peroxide, a radical initiator. And you've probably seen that in OCHEM 1, but we're going to revisit it and explain it using radical chemistry. And then in the last episode, we're going to look at real-life applications because radicals are very important to understand chemically, because when you see it in real life, you're like, oh, for example, refrigerants, old refrigerants called freons, those destroy the ozone in our atmosphere, and that has some pretty bad implications with it. So it's important to understand these things, not just knowing the chemistry, but knowing why it's important to know it. So let's get into what are radicals. Okay, so the big question is, what is a radical? Well, a radical is any atom or any molecule that on one of the atoms or many of the atoms there's characteristic of a singular electron. So for example, this here would be an example of a radical, and I'll just draw in our electron as in red. You can see here this is a radical because there is one electron. How does this happen? How do we form radicals? Well, for example, if we have bromine gas, so if we have bromine gas and we subject it to either heated conditions, although I feel like heat isn't very green, so we'll go with the hellish orange, or we use photochemical conditions, what's going to happen is we're going to see, and until this point, we've only seen bonds break one way or the other. We've seen them break, let's say this bromine would get 2 electrons, or this bromine would get 2 electrons. But with radical chemistry, we're going to see something called homolytic bond cleavage. Heterolytic is what we've been discussing, right? One atom of the molecule gets both electrons, the other one is deficient, right? So like with NaCl in their bond, well, they would have an ionic bond, but when they come together, chlorine steals all the electrons and sodium is sad and has no electrons. But with bromine gas, what we're going to see when we either heat it or put it under photochemical conditions is each of the atoms are going to get 1 electron, and we're going to use these special fishhook arrows or one-sided arrows to indicate that only 1 electron is going, right? Because when we showed arrow pushing, we've shown with a double-sided arrow, right? But we just use 1 to signify each atom gets 1. And as our product, we are going to get 2 bromine radicals. So they look something like that. So 2 important things we want to understand about radicals is first, their geometry, but also their stability. So let's look at their stability real quick. I'm going to draw 3 radicals, and you have to rank them by most stable. And you're probably not going to know, and that's okay, because that's the part of the learning process. So the red little dots here, they signalize that single electron on the molecule. So the trend of stability, is it going to the right or left? Well, it's actually, the stability is increasing this way. So the most stable radical is this one here, right? This one's the second most stable, and this is the least stable, and we'll see why that's important later. As for why, remember about hyperconjugation with carbocations, right? That's what decreases that positive charge, right? Just coming back to kind of show what I'm talking about. If we have a tertiary carbocation, we know that there's these orbitals, right, where there's some electrons, and we know that there's some here, in their little respective orbitals, right? little electrons. And what they're doing is they're running around this molecule. And what that subsequently does is lowers this positive charge. Right? If there's electron density at a place where there's partial positive charge, it's less positive, right? Because there's that existence of a negative charge near there. That's why if we compare it to, say, a primary carbocation, well, we know if we have that orbital there, there's only one set of electrons that are actually going over there and stabilizing this positive charge. So hopefully that makes sense. Hyperconjugation means that radicals are more stable because that singular radical, now it's not as, it's a little different. It's not stabilizing a positive charge. It's the fact that that radical electron can just run around through hyperconjugation. Now for this part, we're going to talk about the geometry. Now this is debated. You can see the figure here. It's saying it could be trigonal planar, or it could be this geometry you probably have never seen called a shallow pyramid. A shallow pyramid is just a hybrid between trigonal planar and tetrahedral geometry. Now, for the trigonal planar, it's simple, and your professor or whoever's teaching Organic Chem 2 might just say, okay, it's trigonal planar. But there is convincing evidence out there that it's not really flat as they claim. It still exhibits almost the exact same properties as we'd see with trigonal planar. And we'll get to that a little later, but basically that one electron just hangs out in an empty p orbital. Kind of like how a carbocation just has that empty p orbital. It allows attacks from the top or the bottom, which we'll see when we get to the stereoselectivity of radical halogenations and stuff like that. But the shallow pyramidal, it's saying, well, you have an electron there. It's not a completely empty. It's not a completely empty orbital, that empty p orbital, right? It has that one electron, and we know that electrons repel each other. That's what Vesper theory is based on. And because of that, we know that there's, or they hypothesize, and there's evidence to support this hypothesis, that there is some repulsions there which causes this shallow pyramidal, and it rapidly interconverts between each other, which kind of gives it that trigonal planar kind of thing where it can be attacked top or bottom. So just thought I'd point that out because it's a really interesting fact and kind of a new thing. So the last thing I want to speak about is resonance stability in radicals. As we'll see, we can add stability to a radical by giving it a conjugated character. So if we have, for example, this molecule here, 1, 2, 3, 4, 5, 6. So we have hexane, and let's put a radical electron here. Let's put a pi bond here and a pi bond here. So we can make, we can show resonance here if we, were to just take this. Hopefully this isn't too hard to see for you, but we can have some resonance. Okay, and then we have this here, an electron here, an electron here, and then we can have our other resonance structure. And although minor, it may still exist and give it some character, because remember, what we're making here is a primary radical, and those are not as stable. So this isn't a major resonance form, but it still is one. And because of the conjugation through these conjugated systems here, we can see that this radical is felt on this carbon and this carbon and the end carbon, although to a minor extent. This means the energy of this radical electron is lower. So this is another important thing. Hopefully you're starting to pick up through the first semester that you've had with organic chemistry. Stability in molecules, and this is just pointing out that radicals, when in conjugation, are a lot less reactive. So that was the properties of radicals. In the next episode, we're going to look at how we can turn simple alkanes, something that wouldn't be very synthetically useful, into very synthetically useful alkyl halides. So make sure to check out that next video.